In this video, we're going to talk about using the Simpsons rule method, which is a parabolic approximation. And we're going to use that to approximate an integral that is difficult for us to solve. So there is a video before this in the series which talks about trapezoidal rule, and I go into a more in-depth discussion about why we use these rules, but essentially it is when whatever we're trying to integrate is difficult to integrate. And so we say, hey, we're going to use this rule, which will get me an approximate value, which is pretty close enough that I can say, well, the integral is almost this. So we determine these y values by plugging in x values that are determined by regular intervals all the way up from x sub 0 equals a and my last x sub n equaling b. And delta x, that is the subinterval length, and that's found by subtracting my upper and lower bounds of integration and dividing by the quantity of subintervals that we wish to create. One thing to note is that n value has to be even. So we have to be dividing into 2, 4, 6, 8, etc., 10 subintervals. All right, and the reason that is because we have a different patterning. So you'll notice that my first y value and my last y value have a coefficient of 1. But in the middle, those y values, we're going to have 4, 2, 4, 2, 4, 2, 4, 2, 4, right? So it's this alternating pattern. So we'll start with 4 of my y sub 1 plus 2 of the y sub 2 plus 4 of the y sub 3. And that is why this has to be even, otherwise that pattern can't be achieved. So it's always those coefficients are going to show up 1, and then we'd have 4, 2, 4, 2, 4, etc., ending with some 2, 4, 1. So it's symmetric. All right, so let's do an example. In this example, we're going to be dealing with the integral from 0 to 2 of 5x to the 4th. And, this is super easy for us to integrate. If I wanted to find the exact value, it would be 5, and I would have x to the 5th over 5 from 2 to 0. The 5s would cancel, and we would have 2 to the 5th minus 0 to the 5th, or 32. So the exact value of this integral is 32. But if my integrand was something very difficult to deal with, this might be a situation where I would choose to use Simpsons rule as an approximation method. And Simpsons rule can get you very, very close, especially if you increase your quantity of subintervals, right? You partition that interval out into more subintervals. And keep in mind that n value, n has to be even. All right, so in order for us to do this, let's look at what delta x is going to be. So n equaling 4, we would subtract 2 minus 0 divided by 4. That gives us 1/2. And all that's saying is to go from 0 to 2, and to break that into 4 subintervals, we would be counting by halves. 1/2, 2/2, which is 1, 3/2, and then 4/2, which gives us 2. All right, so delta x is 1/2. And what would my y output values be? So these are all my x values. So I have y sub 0 equals 5 times 0 to the 4th, or 0. Y sub 1 is 5 times 1/2 to the 4th, which would be 5/16. Y sub 2 would be 5 times 1 to the 4th, or 5. Y sub 3 would be 5 times 3/2 to the 4th, which gives 4/05. over 16, and y sub 4, plugging in 2, is 5 times 16, or 80. So, using my rule for Simpson's rule approximation, my delta x, we said, was 1/2. That needs to be divided by 3. And then we're going to have 1y sub 0 plus 4, looks messy, plus 4y sub 1 plus 2y sub 2 plus 4y sub 3 plus y sub 4. Or 1/6 times 0 plus 4 times 5/16 plus 2 times 5 plus 4 times 405 over 16 plus 80. So what I have done here is really I've just plugged those numbers in to my Simpson's rule approximation. All right, so we're always going to end, that second to the last term will be a 4 as the coefficient, and the last term will have a 1. So let's scroll back down and calculate what that value is. Using my Simpson's rule, if I calculate this entire sum and then distribute, I will get 32 and 1/12. 32 and 1/12 is my approximate value, my approximation. Now, my exact value, because this was an easy integral for us to deal with, we could find that the exact value was 32. And so that is just, notice I left a 1 off there, that is just 1/12 of a difference, right? That's very small. 1/12 is a small amount. And if we looked at determining that percentage of error, that's always going to be my approximation minus my exact divided by the exact, or 32 and 1/12 minus 32. I keep doing that. I wrote 1/12, or I said 1/12, I wrote 1/2, 1/12 minus 32 divided by 32, which gives me 1/12 divided by 32, or roughly 0.0026, or rather 0.26%. So this differs by less than 1/3 of a percent, 0.3 of 1%. And that was just with 4 subintervals. So it stands to reason, as we've learned before, if I increase this n value and make that larger, I'm going to get a far better approximation. We'll get even closer. But 0.3, that's less than 1/10, or less than 1 of a percent, right? So this is a very small amount of error, which is acceptable. And then again, as I said, if that n value is greater and we have more subintervals, then we're obviously going to achieve a better approximation. As always, please email me if you have any questions.